Mr. Sakari Palaspuro to present his paper titled Reference Toughness, a pragmatic tool to estimate ductile brittle transition temperatures. Please.
Okay, so thank you, Mr. Chairman, for the introduction. So yeah, my name is Sakari Palaspuro. I come from the University of Oulu, Finland, and also from the Norwegian University of Science and Technology, where I recently spent almost 3 years doing my PhD study. And my collaborators for this are Dr. Sara Mehtälän from SSAB, Professor Jukka Kömik, who is Chief of our department, and Professors Chilian Chang and David Portman from the NTNU and Oulu, respectively. So, my topic here today is the reference toughness, our concept, pragmatic way to estimate the ductile brittle transition temperatures. And this basis extends a bit from my doctoral thesis that was on ductile brittle transition temperature phenomena in ultra-high strength steels with Aspen's microstructures. And our recent paper on these weakest links, the parameters that govern the toughness in these ultra-high strength materials made by direct fencing. So the main question for this is that what are the cleavage fracture indicators in steels with lat-like microstructures, and more importantly, how to estimate the toughness transition temperatures by using this knowledge. So, to start with empirical findings, here we have a very generic fracture surface, and then when we go zooming and enhancing deeper into the material, we find usually a generic brittle particle that has nucleated failure, the primary failure of the material. And we see that also this grain size that surrounds this particle can play a significant role. And many studies have been dedicated to the estimation of impact toughness transition temperatures. And the key idea behind all this is that decreasing grain size improves, and as with decreasing and increasing yield strength impairs the toughness properties. And when we look at those established equations, we see that they are quite heavily based, also due to the historical reasons, to ferritic steels. And there has been attempts to apply those to also to lat-like microstructures, but we did want to take a different approach to this. So, please bear with me. So, we consider brittle fracture now from the point of view of a local microcrack ahead of the macroscopic crack tip or a notch, depending on the specimen type, and what are the requirements when does this local microcrack propagate and then cause the primary failure in these specimens. And a popular way to assess these is to treat them with this refit criterion. So, how does this then go in the different microstructures? Well, in schematic cases, we have different sets of more and less effective boundaries that can either deflect or arrest the propagated drag. But in the realistic case of modern multi-phase steels, it can be a mess. So, to get from this take to a sample level properties, we use this effective grain size, which simply is the size of these grains with boundaries that can arrest the crack. That is usually with at least grain boundary visualization of at least 15 degrees. That is well known. But in the literature, often it's referred often as the size of pyrosinite parameters, ferrite grains, subgrain blocks, but also those packet planes and cleavage unit sizes and so on. Partly with historic reasons, but also recently there are many studies showing that different features are to blame. And also in real life microstructures we have distribution of grains. So the most used measure is the average grain size, but some recent advances have shown that it's the coarse grain size in the cumulative distribution that plays the key role. And of course, these sort of use like the 80% or 90% level of this distribution. That has been also done with different parameters for decades. But then to go to the experimental part. In short, we have used low carbon ultra high strength steels that are used also for structural applications, and we have made them with varying finish rolling temperatures and the level of austenite and caking to get the range of as-when steels with varying microstructural phase constituents and grain size. And then we utilize the literature to see how this goes in the broader extent. And we have done extensive characterization of these steels, and I want to emphasize that these findings are also supported by the pragmatic evidence. So mechanical tests, we have used the standardized SAR2B impact toughness tests and standardized fracture toughness tests to get these ductile brittle transition temperatures, T27 or T28 joules in the case of impact toughness, or then the T0, the fracture toughness reference temperature from fracture toughness test. And further motivation, the result when we plot our materials, the yield strength and the transition, impact toughness transition temperature, we do not see much. And this motivated us further to take a different approach to incorporate the effect of strain and stress. So I jumped a bit forwards here to show the main result what we published recently in Process Engineering. So it's an let's say a semi-physical approach to estimate the impact toughness transition temperature. So it comes from a local failure criterion as a reference toughness, and then the extent of this propagation as the fraction of 100 cleavage planes, roughly parallel to this crack plane. And with this two-parameter model, we got a very nice fit with our materials. And it was the coarse grain size I used in these cases to really get that. And also, the pragmatic evidence also shows that the grain size around these inclusions that nucleated the failure corresponds to that level of 80 to 90% cumulative distribution. So just a quick comparison of this estimate to this literature. Well, the level is okay, of course, due to fitting with the data, but more importantly, with these two parameters, we are able to capture almost all of the variance in these experimental results. So to jump into this reference toughness idea, we start with the basic K1 stress intensity, but now when we want to address both the cases with a notch and a sharp crack and have the same parameters, we need to modify the stress term. And with the engineering way to address these, we use coefficient F, which is the general ratio between the fracture stress and the yield stress. So for cracked single-edge notch bend specimens, we have used 3.0, so which matches with the small-scale yielding. Then for impact toughness specimens with a notch, we use 2.2, which also has which bases on early analysis, Green and Dundee, and the other one that I forgot, but it also has a good match with the empirical findings from Bosset and others. And then, when we have quasi-static loading of fracture toughness test and dynamic fast loading in impact toughness test, we need to address the change and the elevation in the yield strength due to this increase in the loading rate and strain rate. So this will be used in the function. I'll show you in the next slide. And these then make up the reference toughness that incorporates this effective stress and the crack size as the microstructural parameter as this efficient post-grade size. So around 80% in the distribution, and half of that in our this version of this. So not two cracks, but just one crack. And the elevation of yield strength due to this increasing strain rate is taken directly from this background ductile Eurocode. So that is what I did before here. And because of insufficient data, we have used such the constant 1.2 to materials with room temperature strength of 900 megapascals and more. And with this effective stress, we see that it will form, in the case of cracked pre-crack specimens, it forms an upper boundary to these materials that have been calculated with this criterion of fracture stress. And when the crack size has been taken as the efficient post-grade size or the cleavage fracture unit size, and then they do coincide in the cases what we have studied under the microscope. So, running mostly out of time, so just showing you very shortly what can we do with this one parameter of the propagation of the local micro crack with the sufficient size. With impact toughness, we get with roughly almost 50 samples this nice tight fit, and with fracture toughness tests, we are a bit more limited in our materials, but also get a similar trend with a slightly lower slope. And these are divided by this specimen dependent and notch acuity dependent term. And when we combine, when we use this general ratio between the fracture strength and yield strength, we get this. So this is the main result of this incorporating 69 different materials from impact toughness test and fracture toughness tests. We get this trend for the propagation that has a standard deviation of 18 degrees, but we have also very wide range of yield strengths from 400 to 1200 megapascals, and they have also both advanced state and advanced temporary state materials with varying phase constituents. And with that, I want to thank you.
Mr. Palaspuro, thank you very much for your nice presentation.